Buenos Aires in Argentina. And his talk will be on manipulation of light, heat, and forces on the nanoscales with metallic nanoparticles. So let us welcome our speaker.
Thank you very much. I'd like to thank all the organizers for this invitation. It's a great pleasure for me to be here and have the opportunity to tell you something, some of my work. I have to apologize in advance for not being able to stay longer in the school. Unfortunately, the school caught me in a very busy period. But I think it's a very interesting school from what I can see from the program. So I hope in the next edition of the school I can take part with more time. So I will, as Ivan said, the topic of my talk will be about metallic nanoparticles and how they can be used to manipulate light, but not only light, but also heat and forces at the nanoscale. I will use the two lectures that I have to tell you first, in the first lecture, to give you some overview about the physics of metallic nanoparticles and their interaction with light. And in the second lecture, I will give you some examples of all these topics of my own work. So I hope that works out, and with the first introduction I give you, especially for people who are not from this field, then they can understand better the specific examples I will tell you later. Okay, let's get started. Metallic nanoparticles. So let's consider first a metallic nanoparticle that is very small in comparison to the wavelength of light. What happens if we illuminate such a nanoparticle? Then we have an oscillating electric field, and the electrons, the free electrons in this nanoparticle, will try to follow the electric field. And so they displace from their resting positions. And so basically what we have here is like an oscillator. The electrons move away from the resting positions, the positive nuclei try to pull them back, and then we have an oscillator which natural resonant frequency for most of the noble metals lies in the optical regime. And that's why these metallic nanoparticles have optical resonances. This is not a new story. Actually, I give you here some more or less arbitrarily picked names. Many people work on this, but these are probably the most important works. It started in around 1900 with theoretical work by Arnold Sommerfeld. Robert Wood made the first plasmonic observations in light spectra. Maxwell Garnett and Gustav Nie developed theories, analytical solutions for the light scattering by metallic nanoparticles. And later on in the 50s and 60s, a more complete understanding of surface plasmons came about. And in 1968, a very systematic experimental study of surface plasmons began with the configurations developed by Kretschmann and Alter. So nowadays, all these things are called plasmonics. So if you hear that word, that is very fashionable nowadays, it refers to the science and technological applications of metallic nanoparticles, particularly of the optical properties of metallic nanoparticles. And this technological applications of metallic nanoparticles and the optical properties is not new. Actually, it has been used for many centuries. This is an example of a Roman cup. It's called the Lycurgus cup. It's from 400 years after Christ. And it had the peculiarity that if you illuminate this cup from outside, it looks green, but if you illuminate it from inside, it looks red. And that's due to the optical properties of gold and silver nanoparticles that are embedded in this glass. The same kind of nanoparticles are used actually to color, to stain glasses in the old cathedrals. So the technology, the use of metallic nanoparticles is very old. So but what's new, what's interesting, what can we do today? And this is the outline of the talk. First, I'm going to spend quite some time telling you about the basic physics of what's called the localized surface plasmon resonances. That's these optical resonances of metallic nanoparticles. And then I will tell you how we can use those resonances to manipulate light, heat and forces at the nanoscale. And that will enable new applications that were not possible before. So, what's the theory behind this? If the particle is very small, then we are lucky and we can use what's called a Rayleigh or dipole or quasi-static approximation. And then we consider the field is homogeneous all inside the nanoparticle, just with a certain frequency, and we get these rather simple formulas. We can express everything in terms of the polarizability of the nanoparticle, which is a function of the radius. The size here we consider a spherical particle, but it's so small that the shape doesn't really matter. But so let's consider a sphere. So it's the polarizability is a function of the size. It's a function of the material, the dielectric constant of the metal that the nanoparticle is made of, and it's a function of the dielectric function of the surrounding medium as well. We can calculate the scattering and absorption cross sections. Both are functions of the polarizability, and what we first see is that the scattering goes with the polarizability squared, and the absorption goes with the imaginary part of the polarizability. So here we will see already that the scattering will go with the radius of the nanoparticle to the 6th power, and the absorption with the radius of the nanoparticle to the 3rd power. That's a big difference that will determine several applications later on. If the particle is bigger than this, actually if it's bigger than 5 or 10% of the wavelength, these formulas don't work anymore, and one needs to solve the problem more accurately. For example, with the Mie theory. Here you see, I'm not going to tell you all the details about the Mie theory, it's just solving the Maxwell equations in spherical coordinates. But what I want to show you is that the Mie theory works really well. So what you see here is that in brown is the scattering spectra of an 80 nanometer gold nanoparticle. And the red dashed line is the Mie theory for that same particle. And the fit is perfect. Here there are no fitting parameters. Nevertheless, we're going to use these formulas all along this first part of the talk, because my intention is to give you a feeling, to give you an idea of how these things work. And for that purpose, these formulas are very, very handy. So in most cases, they won't give you quantitative results, but it will tell you what's going on, in which direction parameters work. So that's why we're going to use these formulas in most of the examples to understand the basic physics. If one wants more accurate results, one has to go, and especially for complex geometries and complex shapes, one has to solve the problem numerically, and there are a number of methods to do that. Here I just mentioned you some, in case you're interested to take note and find out more about yourself. I saw there's also an advertisement of a CST studio. That's a very powerful program to perform FDTD calculations. And so these are probably the main three, the most common numerical methods. The discrete dipole approximation. Here we represent our system by a cubic array of polarizable elements, or dipoles. And the green dyadic method is a semi-analytical method, but for that one needs to know the Green's function of the geometry that is being solved. That's in some cases an important limitation. And the FDTD method, it solves the time-dependent Maxwell equations also in a discrete manner. And this is one of the most, in my opinion, versatile methods. And I think with time it will become the most popular. So let's start then talking about localized, this resonance of metallic nanoparticles. What you see here is an image, a dark field microscopy image of silver nanoparticles of different sizes. Dark field microscopy, if you don't know what it is, so it's an optical microscopy technique, very simple. We illuminate our sample with a high angle of incidence, so that if there's nothing scattering in our sample, it looks dark. But if there is anything scattering light, then it will scatter light. So the trick here is that we collect light with a numerical aperture smaller than our illumination numerical aperture. So none of the light that we use to illuminate goes to our detectors, unless there's something scattering on the sample. That's why the background looks dark, but where we have some scattering point, then we see light. And those scatterers here are silver nanoparticles. And if we use white light to illuminate, then we see that these nanoparticles shine up with different colors. And the reason for those different colors is the different sizes. So what we are measuring here is scattering of the nanoparticles, and we learned that if we look in the Rayleigh regime, you would say, yeah, it depends on the size, but only the intensity. The resonance condition, which is here, it should not depend on the size, right? That's a failure of the Rayleigh regime, because these nanoparticles are larger than 10 nanometers, which would be the limit for the Rayleigh regime. So if we go beyond that limit, the resonance frequency also depends on the size. We'll see that in the next slide, or a couple of slides later. So the first take-home message is the resonance condition depends on the size. The second concept is that the resonance condition also depends on the dielectric constant of the surrounding media. Here, this epsilon m. What you see here is the resonance spectrum of one silver nanoparticle, and as a function of the refractive index of the surrounding media, simply changing from air to water, alcohol, and so on, we see how the resonance shifts. And here you see the maximum of the resonance is more or less linear with the refractive index change. Okay, and finally, the position of the resonance also depending on the shape. Why is that? Well, you can think, here we have the electrons that have to move in this oscillator, but those electrons are also constrained by the shape of the nanoparticle, and that will change the natural frequency of these resonators, which are the nanoparticles. So that's more or less what's going on. So we have electrons that move collectively in these nanoparticles driven by the optical field, and the resonance frequency will depend on many aspects, on the material, on the shape, on the size, and on the surrounding medium. And those resonances have 6 main features that will determine the possible applications that we can think of. These 6 main features are the spectral response. So where if you want the color of the nanoparticle, at which wavelength they are resonant. We saw that there is an enhanced absorption at the resonant frequency. So these nanoparticles, if we illuminate them with the right color, they will absorb a lot of light. They are very bad light emitters, so almost all light that is absorbed turns into heat, so there will be heat generation by these particles. There's also an enhanced scattering, so they will scatter light very efficiently at the resonant frequency. In addition, there will be an electric field distribution around the nanoparticle, characteristic of each resonant mode. This is what I tried to show you here on this cartoon. So if you have a sphere and we illuminate with an electric field like this, then we will get this symmetric dipolar pattern. But if we have a triangular prism nanoparticle and we illuminate with the same direction, we will see that the field gets more concentrated in the tip. So there is a specific field distribution for each resonant mode. And finally, there is directionality. So you can see that here, for example, light will be scattered in these directions, but no light will be scattered in that direction. So there is some directionality, which in this case is very simple, but if we go to more complex shapes of nanoparticles or systems of nanoparticles, the directionality can become more pronounced. Let's see some trends about localized surface plasma resonances. The first thing that what I try to show you here is we just consider a sphere, a silver sphere, of different sizes. So we just change the diameter of the sphere, and we see that in this case, we see one sharp resonance, and so in black you see the extinction cross-section, in red the scattering, and in green the absorption. So we can differentiate the two contributions to the extinction, and we see that for a small sphere, the contribution of scattering is very small. It's mainly dominated by absorption, like we expected from the Rayleigh formulas, due to the dependence with the power of 3 and power of 6. So if we increase the size, we see that now the absorption goes down a little bit, the scattering becomes more important, but we also see a shift in the resonance. If we would close up here and take a look at the maximum scattering wavelength, we will see it's shifting by some nanometers. Here the shift is more pronounced. That's the failure of the Rayleigh approximation that I told you before. And if we consider a very big sphere, like 100 nanometers, then we see, first, that we have multiple resonances. These are the higher order resonant modes, the quadrupole and octupole, so this sphere is big enough to accommodate high order resonant modes. And we also see that the scattering now becomes dominant. So the take-home message here is for small nanoparticles, the resonance is dominated by absorption of light. For larger nanoparticles, it's dominated by scattering. And the LSPRS, the LSPRS redshift with increasing size. And we also can see that higher order modes appear at shorter wavelengths. Let's take a look now at the electric field distribution for each of these resonant modes. As I told you, there's a specific field distribution around the nanoparticle depending on the mode that you are exciting. If we take a look at this example, this is a 200 nanometer silver sphere. So it can accommodate a dipole resonance here, a quadrupole resonance, and an octupole resonance. And we see the dipolar, in this case the sphere is illuminated with the plane wave from this direction, so it's a little bit asymmetric. But we see, in this case, when we excite with the wavelengths around here, we see clearly a dipolar pattern. Now if we excite here, we see a quadrupolar pattern. And if we try to excite the octupole, we don't see it here because the contribution is very small. And you have to be aware that we are also exciting at the same time the quadrupole and the dipole mode at the same time. Here we cannot avoid it in this case.
Yes. Question. So this is a gold sphere?
This is a silver sphere.
Silver sphere, and the excitation is what wavelengths?
In the three cases, is three different wavelengths. So this one is excited here to see the electric field distribution of the dipolar resonance. This one is excited here at the peak of the green to see the quadrupolar resonance. And the last one is excited here to try to see the field distribution of the octupole resonance. But we don't see a much difference because we are also exciting a lot of the quadrupole and the dipolar resonance. So in this case we cannot separate these modes, but if we use rods, for example, so a small silver cylinder, then the higher order modes appear much more separated. Like here you can see the dipolar, the quadrupole, the octupole, and higher orders. And in this case we could excite them selectively. If you have any questions during the talk, just stop me, and let's do this as interactive as possible. Okay, one next feature of this resonances is that they can couple. If we have two nanoparticles not close enough to each other, they interact electromagnetically and then they act as a single oscillator. And in that case, the resonance shifts to the red, just as it would happen in a heavier oscillator. But in addition, what we see is that we get fields, electric fields, that are much more confined and stronger than in the case of a single nanoparticle. Here you see the example, again, a single silver sphere, the field distribution is dipolar in this case, and like we saw before. And now we have two spheres, and we in the same direction, and we see that the field is much more enhanced here in the gap. Here you see the intensity of the field with respect to the incident field. So here it's in purple is 10 times larger. Here in yellow it's 70 times larger, and it's highly confined to the gap. A few words about how to detect small nanoparticles. I showed you the dark field technique. That's one of the most widely used techniques because it's very simple. It's a far field technique, and one needs almost nothing. We can use even lamps, incoherent light. But there are other techniques that are able to detect very small nanoparticles. The dark field technique is based on scattering, and if the scattering cross-section goes to the radius to the power of 6, so it goes down very quickly with the size. So for nanoparticles below 40 nanometers, one cannot see anything. If we aim to detect smaller nanoparticles, we can use, for example, this interferometric technique, which is based on the interference between the field scattered by the nanoparticle and a reflected field. And then we see that depending on the size of the nanoparticle, we get a positive signal or a negative one, and this is due to an interference term between these two fields. Another possibility is to use what's called photothermal techniques. And this is a clever idea that has been developed photothermal heterodyne detections in this case. It's a photothermal technique which basically what you do is you transform. We saw that the scattering goes down very quickly with size, with the r to the power of 6, but absorption is, becomes dominant for small nanoparticles. So what you do here is you transform the absorption into scattering. So you use a laser that can heat up the nanoparticle. The nanoparticle increases the temperature of the medium around, and that changes the refractive index. So what you do is you produce a scatterer around the nanoparticle due to this change in refractive index, and you detect that scatterer. Furthermore, you can switch on and off that heating, so you can produce and destroy that scatterer and use lock-in detection to detect that scattered signal, and that's very, very sensitive. Here you see an example from this paper, and those peaks you see here correspond, the big ones, to 5 nanometer nanoparticles, gold nanoparticles, and the small peaks correspond to 1.4 nanometer nanoparticles. That's only 65 atoms, or something like that. So with this technique, you can detect very small particles. Okay. So I hope you got now a flavor of what these localized surface plasmon resonances are, the basic features of them, and now we will start discussing examples of how they can be used to manipulate light, heat, and forces. So let's start with light. So basically what we are going to use here is that near field distribution that I showed you to manipulate light-induced processes on the nanoscale. Why on the nanoscale? Because those fields are very small and strongly confined to regions that are even smaller than the nanoparticle. So these fields have been used widely for surface-enhanced Raman scattering, so I'm not going to talk about this. They are also being used for fluorescence, excitation, and emission, for optical antennas, sensing surface reactions, and for nonlinear optics. So here I will tell you about these 3 topics, for which I will give you in my next lecture some real examples. So let's see. Let's talk about the fluorescence. So for those of you, I guess there's no one, but just in case, to remind you what fluorescence is, in a very simple picture, we consider 2 systems, 2 electronic states, a ground state and an excited state, each of them with some vibrational structure. And so this could be the simple picture of a molecule that, if it absorbs light, an electron can undergo an electronic transition to a higher electronic state. That happens very, very quickly, in femtoseconds. Then some intramolecular vibrational relaxation takes place that puts the excited state in the ground vibrational level. This happens in picoseconds. And later on, some nanoseconds later, the molecule can relax back to the ground state by the emission of a fluorescence photon. This photon has a different energy because of this energy loss, so usually the fluorescence light we detect is redshifted with respect to the excitation. Okay, so what do metallic nanoparticles have to do with this? Okay, before we go there, let me give you just few words about reciprocity. I think this is an optics community and we are all familiar with reciprocity. So, but just to remind, what is this about? So imagine you have a point dipole somewhere in space, and we check the electric field this dipole is producing at another point. Well, reciprocity tells us that if this dipole generates an electric field along some direction, very large for example, then if we put a dipole on that point, along that direction, then it will do the same on that other point. That's reciprocal. Why do we care about this? Because in many cases with metallic nanoparticles, it's easy for us to calculate those field distributions that I showed you. So we illuminate the nanoparticle from a certain direction and we see what kind of electric fields are generated around. But now we are going to be talking about fluorescence, where the opposite takes place. We will have a molecule in that spot emitting light, and we want to know what's going on. Where is that light going to go? What's the probability of light emission? And by reciprocity, we can calculate that light emission by calculating electric fields. And that makes things much easier. So if we go back to the fluorescence picture, the simplified fluorescence picture, we have basically these three rates. The excitation rate, so that's the photon absorption rate by the molecule. And then once the molecule is excited, it can go back to the ground state with the emission of a photon. We call that the radiative rate. But it can also do it by other processes, by interactions with solvent, by wasting its energy in vibrational motions, etc. So that would be the non-radiative rate. So if we look for a fluorescent signal, or better said, the total intensity of fluorescence that is emitted, that would be the product of the excitation rate by the quantum efficiency, and that is the ratio of the radiative rate divided by all the decay channels. In this case, we consider only these two. Okay? And this radiative rate will be proportional to the photonic mode density. So here is where the reciprocity is important. So the excitation rate is given basically by the absorption cross-section of the molecule and the electric field at that point. So if we have a molecule in one of these hotspots, in these regions around the nanoparticle with a very strong electric field, the excitation rate will be higher. If the molecule instead is in a place where the field is blocked by the nanoparticle or damped, the excitation rate will be lower. Now by reciprocity, we can calculate those fields at the emission wavelength of fluorescence, and in that case, the regions where we have a strong electric field will be regions where a molecule will emit more efficiently. Simply because the photonic mode density will be higher, and then the probability of emitting a photon for that molecule will be higher. In practice, you will see many times if you read papers that the fluorescence was quenched or the fluorescence was enhanced, and that's people love to try to get huge enhancement factors and say we couple a molecule to a nanoparticle and fluorescence is 10,000 times stronger. But you have to be aware that that's not so easy to really to determine, because many things are going on and many particles may be influenced by the nanoparticle simultaneously. Okay? So a nearby nanoparticle can influence the excitation rate, as I told you. And a molecule, a fluorescent molecule, can be in a spot where the electric field is high or the electric field is low. But furthermore, a molecule will absorb light only when a fluorescent molecule works like a dipole. So that electronic transition that I showed you in that simplified picture is actually an electronic transition, and the molecule has a transition dipole associated, so it will absorb light only if the molecular dipole for absorption has a strong component aligned with the electric field. So when you work with these nanoparticles, I showed you those electric field distributions, that was the total field. If you want to see the interaction with the molecule, you have to consider the component of that field along the molecular dipole. So you may have a very strong field, for example, 10 times stronger than the incident field, but if it has the wrong orientation, the molecule will not be excited. So that's something you have to take into account. But that said, a nanoparticle can influence that rate, can make it several times higher and can make it several times lower as well. The radiative rate is also influenced by a nearby metallic nanoparticle because of the photonic mode density. That's analog to the excitation rate if you want, but at the emission wavelength. And here you have to consider the right component of the electric field as well. And in addition, it can influence the non-radiative rate. So if an excited molecule is very close to the metal, a nanoparticle or a film or a bulk metal, then direct energy transfer can take place, and the molecule goes down to the ground state and by generating lossy currents in the metal, and then the fluorescence is gone. This takes place at very short distances, so up to 15 nanometers more or less, typically. And finally, a nearby metallic nanoparticle will modify the angular, not only the emission, the angular excitation and emission. So this is very important in experiments when you have a limited, so you illuminate your sample from one side normally, from one direction, and you collect your light with a limited numerical aperture, right? So if you want to see what's going on in terms of quenching or enhancements, you have to watch out that you are exciting and detecting from the right direction, because you might be losing your signal or your excitation just because you are exciting in the wrong way.
Can I ask a question?
Of course.
You're assuming molecules are fixed and they are normally moving around
Well,
all kinds of states.
yes, they are moving, of course, makes things more complex, and what you have to do is to make a time average of.
But if it's totally random, the orientation of molecules would be like essentially isotropic.
Yes. Yeah. You have to, in that case, take into account the total field in all directions. But that's true for the excitation and the radiative rate, because that's just the total field. The directionality doesn't care about the orientation of your molecule. The directionality is determined by the nanoparticle or the nanoparticle array. Okay? So basically, imagine you have a molecule that is rotating like crazy near a nanoparticle, and it does it very fast, and in your fluorescence experiment, you excite and detect photons many times, so you're probing all these possible orientations. Still, it will couple to your nanoparticle system only when it has the right orientation, and it will emit light as the nanoparticle system is dictating, if you want. So the directionality is still. All right. Any other questions about the light and the fluorescence before we move to heat? Okay, this one is simpler. As I told you, the nanoparticles, metallic nanoparticles, are very bad fluorophores. So basically, they absorb all the light, and the chance to emit a photon is very low. So all the light they absorb turns into heat. What you see here is a calculation. There are still no methods to measure temperature in such small volumes with this resolution, but the calculations are very accurate because we know very well how much light the nanoparticle absorbs, because we know the cross-section very well, we know the laser intensity, we know the thermal constants of water in this case very well. So basically there are no big sources of error in this kind of calculations. And what you see is that when we illuminate, in this case it's an 80 nanometer gold nanoparticle with moderate intensities, we get a very high temperature at the nanoparticle surface, which then decays rapidly into the surrounding medium. So we have a very localized increment of temperature. And depending on how intense is our light source and basically on how much light the nanoparticle absorbs, we can find different regimes. So if we do this moderately, we are here, we heat up the surrounding medium nicely. But if we do it with short laser pulses, with very intense short laser pulses, then we can have cavitation effects and generate small bubbles around the nanoparticle. If we use higher laser intensities in a continuous wave or long pulses, the nanoparticle has no time to, it's not enough the heat that you can dissipate, and the nanoparticle can melt and change shape and things like that. And if we use very short pulses with moderate intensities, we can make and measure coherent lattice oscillations in this nanoparticle. So this kind of heat generated by nanoparticles, here what you see is a temperature profile from the nanoparticle surface for different excitation intensities. So what you see, and even in small regions we can get to temperatures, this is in water, we can get to temperatures above 100 degrees, but water is not melting that thing, so these are very small regions, and if you go to the extreme you can start thinking what the concept of temperature really is in those small regions, but nevertheless we can heat up the water in very small regions. And the other thing is that time is very fast. So what you see here is the time, the temperature, the change in temperature is a function of time from the moment we switch on the laser. And you see that in a few hundreds of nanoseconds we have a steady state. So we have with these nanoparticles now we have a remote controlled heat source with a nanoscopic size that we can switch on and off simply with a laser. And that enables a number of applications. For example, people have used this heating mainly to destroy things, to destroy vesicles or capsules, to perform controlled release, to destroy cancer cells or other diseased cells, and use them as a therapy agent. But also they are being used for more productive or non-destructive, let's say, applications like performing nanoscale thermodynamic experiments and to do local catalysis and processing of materials. So later on in the second part of my lecture I will give you an example of a nanoscale thermodynamic experiments that we did using gold nanoparticles. Okay, and finally about forces. So you're probably familiar with the optical forces. The right way to calculate them is you need to solve the problem and calculate this Maxwell stress tensor and then integrate it around an area that encloses your object, and that will give you the forces, the optical forces acting on that object. So if you want to do that, again you need to do it numerically and solve the problem with one of the methods I mentioned at the beginning. But again, you can say, okay, let's do it simple and use the Rayleigh approximation, and once again, it doesn't work very well, but gives us some knobs, some parameters to understand what's going on. And in that approximation, we see that the time average force on a nanoparticle, in this case a very small nanoparticle, involves the gradient of the field intensity and, okay, here the vectorial product of the field and magnetic field, and again the polarizability. So here you see the magnetic field is normally very small, so basically what we care about here is that we have the real part and the imaginary part of the polarizability and the gradient of the electric field intensity. So this is the called gradient force. And this term here can be, in this approximation, separated in a scattering force and an absorption force with very simple formulas. So basically we have these three forces to take into account. Okay, and if you think of the main application of optical forces is optical trapping, right? And people then, that's why the usual condition there is that you will usually read that the gradient force has to be larger than the absorption plus scattering force. Because this guy, if the real part of the polarizability is positive, will bring a particle into the regions of high field intensity, to the center of a focused laser beam, for example. But this part, this alpha prime, the imaginary part of the polarizability, those are the losses, that's always positive, and will pull your nanoparticle away from your laser beam. So if you want to trap something, this guy has to be stronger than that. In metals, though, we will see, we already know that this guy is negative, and then in some cases, now we will see, and then optical forces may be tricky if you want to trap a metallic nanoparticle. So if you think of how metallic nanoparticles and optical forces are involved, there are mainly two ways. One is to use those local fields that I showed you, the near field distribution around metallic nanoparticles. Those fields are very confined, so they have very steep gradients, and therefore they can produce very strong forces and can be used to trap things. This is an example. These two papers used very similar geometry, where they had two metallic rods and that very strong field in the middle, like I showed you at the beginning with the two spheres, and they can use that to trap dielectric nanoparticles. So here you use the fields of the LSPRS to produce optical forces on other objects, and the other side of the story would be to use a laser beam or some other fields to trap or manipulate metallic nanoparticles. So basically this is known, it's the same story, you just need to know what the field is. Here, as I told you, you have to consider some things, because metals can be very different, and let's go back to these forces with the polarizability. So this gradient force, this one goes always in the same direction, it just pushes the nanoparticle. But the gradient force, the one that you want to use to trap things, goes with the real part of the polarizability. And let's take a look what happens with silver and gold. This is the polarizability normalized to the size of a sphere, again in the Rayleigh approximation here, but just to have an idea of what can happen. In the case of silver, that's a metal with low losses, we see that the real part of the polarizability, so we see always the imaginary part has this resonant behavior and the real part is like the derivative, but depending on the losses, the real part can go below zero. And that means that the gradient force becomes negative, and that will expulse your nanoparticles from your focus. So, if you want to trap a silver nanoparticle, you won't be able to do it here. Why? Because the gradient force expulses your nanoparticle, and the scattering plus absorption force is also pushing it away. If you are at the plasmon resonance, the situation is even worse because the scattering force is huge and you have zero scattering force in any direction. So here it's impossible. In this case, you could think of dark traps, with donut beam that the nanoparticle will push to a minimum of intensity, but here it's impossible. Now, if you are on the red side of the resonance, then the situation is much nicer because you have a very large real part of the polarizability that gives you very strong gradient forces, and the imaginary part goes down almost to zero. So, in fact, trapping nanoparticles here is very efficient, and you can trap very small particles. Dielectric particles have polarizabilities that are much smaller, and normally you have to trap big things. In the case of metallic nanoparticles, because of this large polarizability on the right side of the resonance, then you can trap very small particles. That combined with the fact that you can see small metallic particles, because if you want to have an optical trap, you need the feedback opposition, that enables effective optical trap. And look here, the case of gold is very different. Here the losses are very large, and we don't have, so basically the real part never becomes negative. So here you can trap the nanoparticle if you want everywhere, but again it's much more efficient here, because for the case of gold we have strong losses even below the resonance at higher energies because of intra-band transitions, but here you see the situation is very favorable if you would like to trap a metallic nanoparticle. Okay, I think with that comes to my second part of the talk. I don't know if you want to make a break or
Maybe 5 minutes.
Or some questions about the
Questions, please.
So this mainly is the theory, like it's like calculation, simulation.
This?
When you have a picture about the temperature.
Yes, those are
200 nanoseconds. Yes, the one who shows.
yes. That's solving the heat transfer equation, assuming you have a point source that dissipates a number of watts that you know from the light absorption. That's all. So it's a very simple.
Are there any experiments somebody tried to measure something similar to the temperature of the
Yes, people have tried, but what is it? But you have to, if you look, the region that you're heating is very small. So after 200 nanometers, there's nothing. And there are no methods currently to measure temperature in such a resolution. So you cannot. If you use higher laser intensities, then the region can be visible. People have done it, for example, using temperature sensitive dyes, and then they can see how the color changes or the spectrum changes. But when this region gets to some microns, and then they can extrapolate to lower laser intensities. So that's.
I have a question. So the heating effect, is it most efficient only in the wavelengths of surface plasmon resonance, or can you get strong enough heating also if you are substantially away from that wavelength?
It's given by the absorption cross-section.
Right, okay.
Exclusively. So if you have something like in general, the answer would be at the plasmon resonance is the maximum, and you should aim that. Like in silver, you see you have almost no absorption. Okay, this guy gives you the absorption. You have no absorption if you go too far away. In gold, you still have some absorption due to, this is not due to the plasmon resonance, but
What if you go?
it becomes transparent. The metal becomes transparent, absorbs no light, there's no heating. So,
Can you have multi-photon processes?
for heating.
Yeah.
So, yeah.
For absorption.
Yeah, in principle, I don't recall now what's the 2-photon absorption cross-section of nanoparticles like this. But if they absorb light, they won't emit, that's for sure. It's very, the quantum yield, I mean, it's very low, so the heating is significant.
More questions? If not, let the thing go speak and let us try to reconvene in 5 minutes.